Today I'm going to be discussing Pascal's triangle and all that comes with it, the history, the pieces of it, the structure, and the importance and the impact of Pascal's triangle. So to begin, I'll begin by discussing Blaise Pascal himself. He was born June 19th, 1623 in France. He was a French mathematician, physicist, inventor, writer, and Catholic theologian. He was a child prodigy, which led to him being educated by his father. Um, Also, due to his poor health, he had to be monitored closely. Some of his major discoveries were Pascal's calculators and Pascal's triangle, obviously, but this was not the only thing he contributed to mathematics. He contributed many amazing contributions. He did die in August 19th, 1662, after his poor health finally caught up to him as he aged. So Pascal's triangle is an extremely fascinating mathematical topic that flows into many realms of mathematics, including but not limited to calculus, probability, and geometry. So the origins of Pascal's triangle. Pascal was not the person who originally discovered it. He was the person to contribute a great deal to it and get claim over it after writing a paper about it. So originally it was just discovered independently by the Persians and the Chinese during the 11th century. So the Persians discovered it and the Chinese discovered it around the same time, just not together. Chia Hassan is a Chinese mathematician who focused greatly on squares and cube roots of numbers that were in Pascal's triangle. Omar Khayyam was a Persian mathematician, and he also used the triangle to extract roots of numbers. And Yang Hui was a Chinese mathematician who put a name to it. It's called the old method, and he also was the one to come up with the earliest display of it, which is pictured to the left over here, um, and it's pictured in Chinese um, numbers at the time. So I'm going to be discussing the structure of Pascal's triangle. As you can see, it is an interesting structure. We're focusing on diagonals, the symmetry, horizontal sums, exponents of 11, the squares that it can produce, Fibonacci sequence, and odds and evens that are involved in the triangle. So to begin, I'll talk about the diagonals, which predominantly focus on the first diagonal, which would be the ones, which is literally just a diagonal of ones. And then you have the second diagonal, which is counting numbers, which is 1, 2, 3, 4, 5, 6, and so forth. And it continues down. And then you have the triangular numbers that are predominantly focused on such things as triangles and other geometric situations that have to do with triangles. So horizontal sums, when I talk about horizontal sums, I'm talking the rows of Pascal's triangle. When added together, so each row, so 1, 2, 4, 8, 16, it continues down, and it is doubled every time, so that would indicate that there are powers of 2, which is honestly kind of fascinating to think that it just flows that way naturally when written out. And then the exponents of 11 are also in the triangle. They're across the rows as well. And instead of adding or anything like that, you literally just have to read them until you get to 11 to the fifth, is when you like add the tens over and you have to do some addition to figure out what the number would be. So when I say exponents of 11, 11 to the 0 equals 1, 11 to the first equals 11, and you just read it across, and you'll get the exponent that you're looking for 11. So squares, so like 2 squared, 4 squared, so forth. I'm going to be focusing mainly on the second diagonal when discussing this. The second diagonal, so if you pick a number in the second diagonal, so like 4, So you have 4 squared. You want to find out what 4 squared is. So it's going to equal the sum of the number to the right, which in this case is 6, and the number directly below those two numbers, which is 10. And 6 plus 10 is 16. And as we know, 4 squared is equal to 16. And this would work also with 3. You have 3 squared would equal 3 plus 6, which is equal to 9, which 3 squared is 9, as we know. So the Fibonacci sequence is indicated in the diagonals of Pascal's triangle. So when you add the diagonals in a certain manner, you can find Fibonacci sequence within the addition of them. So Fibonacci sequence is 1, 1, 2, 3, 5, 8, 13, and it continues on. And when you look at the picture, you'll see how that is indicated by the lines in the image. So odds and evens. This is a little, it's based on another triangle that was discovered. It's called Sierpinski's triangle, which is basically taking a triangle and dividing it out into 4 sections, and you keep going and going and going until it's as small as it possibly can be. And when you fill in in this case, the even numbers on Pascal's triangle, those would be the white areas. That is how you get the picture of Sierpinski's triangle, because those will give you the inverted triangles. So Pascal's triangle is extremely important to mathematics because it has so many assets to different areas of mathematics. Calculus, probability, and geometry are the 3 main ones. Probability, combinations and permutations, it's all within the triangle. In calculus, mainly it's the binomial expansion theorem that they reference. It's also one of Pascal's most influential finds in mathematics. It was named after Pascal, finally, when he completed the Trait des Triangles arithmetic in 1654, which was basically everything he knew about the triangle at the time. He used it to make sense of binomial coefficients, triangle properties, and applications, which was extremely important at the time. As we all know, triangles are extremely important to mathematics, and they've helped many areas. So the impact of Pascal's triangle. The mathematical discoveries that have come from Pascal's triangle lead to many properties in calculus, probability, and geometry. Without these discoveries, the way we understand mathematics would be completely different. Like, we wouldn't understand triangles the way we understand them. Calculus would not have the same principles that were needed. We might not even have a full contribution to calculus. The idea of it would be completely different. I feel the main part of it is to remember that this was a thing before the 1600s. It was a thing in the 11th century. So 6 centuries before Pascal even was born, it was known just in different parts of the world and not able to be readily available to the public. I found that this was an extremely interesting topic, and Pascal's triangle is an extremely influential piece of mathematical discoveries. And yeah. And this is my bibliography, and that's it. Thank you.